Hey everybody, how's it going? My name is JP, and today I wanted to talk with you guys about the math behind the Diffie-Hellman algorithm. This is a critical algorithm as part of computer science that was developed back in the 70s to help with the generation of a secure key, which can be exchanged, one can say, or kind of independently generated by two parties in order to start the communication chain of wanting to talk securely with one another. So it's pretty important, and there's a lot of videos and materials kind of covering this on YouTube as well as other sources on the internet. But one thing that I didn't really find personally was a more in depth explanation of the math sort of deriving why the algorithm always works. And I guess I'll talk about this on the next slide, but um, along with some assumptions, is probably the reason why I wanted to create this video. So the prerequisites that kind of is assumed going in is that I assume you are familiar with the general idea behind the Diffie-Hellman process, meaning sort of what Alice and Bob do, kind of the general procedure, because I'm not going to cover that in this video. And there's tons of videos, really good ones by Computer File and other creators that explain this, using many analogies. It's pretty helpful to see. And then I also assume you're kind of moderately familiar with generic math principles, including the binomial expansion, which we'll be using to show that everything works. So what I want to do is kind of better explain the notion of modular math first. And if you're super familiar with this, comfortable with this, you can actually kind of skip it to where I summarize the three equations or three properties that we derived, and then that would show you how it works after that. But I think it's good to kind of review this in more depth. And I also want to show you that in general, the two parties involved in the Diffie-Hellman key exchange will obtain the same key regardless of the numbers actually chosen. So like I said, since most of the explanations that I've seen either overly simplify the math and possibly kind of like glance over some details, leaving the viewers to question what happens to the gaps in between, or they kind of show you an example with some simple kind of numbers, it sort of left at least me wanting to know that can this work in general. And so here I ended up obviously solving it on paper, but here I just want to walk us through how it does actually work in general. Some assumptions. I won't really delve into details regarding prime numbers and cyclic sets and the role of these entities in the Diffie-Hellman algorithm, although these are very important and are frequently implemented. The actual math doesn't really require that they exist to end up working. So I'm not going to really go into that here. And we will be working exclusively with non-negative integers. So whenever I'm talking about any number really, I'm talking about 0 and above, and mostly whole numbers greater than 1. I'm not talking about like 3.5 or anything like that. And I'm going to use the percent sign as my notation to represent the modulo operator. So some people familiar with the a mod n terminology, but I'm just going to represent this as a modulo n. This is actually how I really do it on paper as well. I think it's kind of cleaner. So, what is a modulo or modular operation? And essentially, this operation, when applied to a number a by a modulo n, returns the whole number remainder of a divided by n in the sense that we normally know division to be. And what's important is it does not return the decimal fraction of this division. So basically, let's say, 10 divided by 3. We all know that's going to be like 3.3333. So the modulo does not return 0.333333. What it does return is 1 because it essentially strips away as many 3's from 10 as it can. So it strips away 1 3, you get to 7, 1 3, you get to 4, 1 3, you get to 1. And now when it can't strip away any more 3's, then it returns that whole number remainder. So that's kind of the basis behind this. So if we write a as a number a, a whole number, is equal to I, where I is any positive integer, and this could be 0. So I guess I should say non-negative integer. N is the modulo that we're working in, plus some alpha. then we note that A modulo n is equal to alpha. And we call alpha the residue of A in modulo n. Because when this modulo works, all of these multiples of n will go to 0 because you're stripping them away, and what you're left with is alpha. And obviously we're assuming that alpha is less than n in order to represent this as A. So I will use Greek letters to represent these residues throughout this entire video. And I will also use I, J, K as indices to represent non-negative integers 0 up to infinity as well throughout this video. So we notice a few things. First, the residue alpha must be less than n. And so for all cases, alpha must range anywhere from 0 up to n, but not including n. So it's really up to n minus 1. And second, if a is less than n, then the modulo operator simply returns a. And what we mean by that is if a is less than n, then a modulo n is equal to just a, which is equal to just alpha, because it assumes that the I times n portion was 0, because if it wasn't 0, then it would be greater than n when we're adding any positive numbers to it. And the third is if a is equal to n, or really any integer multiple of n, then the modulo operator returns 0. And so, a mod n equals n mod n if a is n, and then that's just 0 because you're stripping away n and you're left with nothing. And so similarly, if it's just any multiple of n, you strip them away until you get nothing. So there's no remainder, there's no residue, so it's always 0. And so then we notice overall that no answer of a modulo operator can ever be n or greater. So a modulo n will never ever be n or greater. So this means we can represent it as something famously known as the modulo clock, where basically we have this clock-like circle structure thing, starting from 0 up top, 1, 2, ... all the way around to n minus 2, and then finally the last node is n minus 1. And this tells us what values can exist as the answer to a modulo operator. And the way this works is, again, we can write any whole number a as a equals in plus alpha, where alpha is the residue and thus assumed to be less than n. Otherwise, it would be part of this. And when we compute a mod n, we notice that each in simply revolves around the clock one full circle and thus returns us to position 0. So if we start at 0, each in here of this a will just go around and bring us back to 0, around and bring us back to 0. So it won't really count for anything. Thus the answer becomes alpha, which we said must be less than n, and thus a spot on the clock. So let's say alpha is 5, it might be like somewhere here or something. So basically every full rotation of n kind of gets discarded, and then the residue is the answer that we're left with when we take a mod n. So this is meant to show you that alpha is less than n, and it ends up somewhere here on this clock, which is a valid number for it to be. So let's obtain 3 important properties we will need to proceed with this video. The first is a is equal to in plus alpha, which we know, and so a mod n is equal to alpha, and then alpha mod n is equal to a mod n, because alpha is a mod n, because this mod n here carries to here. And we know that this will just be alpha, because alpha is less than n, and so any number less than n mod n just returns that because there's nothing to strip away. So it's interesting to note, but this actually comes out to be true, which is that whenever we have any number a and we do mod n, we can actually do that like as many times as we like, sort of on the result, just apply the mod again, and then on the result apply the mod again, yada yada, keep applying the mod, and it will return the same exact answer, because the first one gives us the residue alpha, and then doing it on the residue however many times you want will just keep giving you the residue because it's less than n. So this is a pretty cool relationship to hold. You can't do it 0 times. Obviously a mod n cannot be a in general. So it's at least once, but after once, you could do it as many times as you want. So let's try to get the second important relationship that we need. And here, let's take a look at a plus b, and then kind of mod n that quantity. So, one might think, well, if we go back and think of it as a division, maybe it's distributive, like a normal division would be. And so it may be the case that this can just be distributing the mod n over to each of the parts of this quantity. Well, that's not the case, and we can see that from an easy counterexample. So let's say a and b are both n over 2. And so if I'm using the arrow because I don't want to put equal signs because it's not equal. So let's say we do distribute. We get n over 2 mod n plus n over 2 mod n. So we just distribute this over. Well, then each of these is less than n. So those will just return themselves. And then so when you add them up, it'll be n. But actually, if we go ahead and truly compute what it is, which is n plus 2, n over 2 plus n over 2, we get n, and then that mod n is 0. So these two answers are incompatible, and so we know it's not simply distributive. So again, focusing on this, let's try to see how we could find out what it is. So it's easier to think of it with parts broken down. So again, we should always be writing kind of things like this when we want to think about things in the modular context. So a could be written as some integer times n plus the residue alpha. And b can be written in the exact same manner. Obviously, it could be a different number of times that we multiply n, so we'll use j for that, and then a different residue we'll use beta. So in that case, this original equation can be written as this, because now everything on the inside is these two, so we sum them up, mod n. Now let's go back and think of our clock. So a bunch of full turns of I times n and j times n don't do anything and bring us effectively back to 0. So this bunch of times going around the clock brings us 0, this same exact thing. So really, the only the sum of the residues, this part of this whole part of the equation, are what move us meaningfully on the clock. But the critical thing to note is that while each residue, alpha and beta, is smaller than n, their sum may not be. Therefore, distributing blindly, saying, let me distribute this mod n to both of them, may lead us to a number greater than n, because when I distribute this, it'll yield alpha and beta because they're both less than n, and then maybe their sum will be greater than n, but that's a no-no because anything greater than n in here should be less than n when we apply the mod to it. So therefore, the key is to always repeat the modulo at the end to ensure we remain in the valid range. And so what I mean by that is we go around, a bunch of times in the circle, stripping away all the I ends and the j ends. And then let's focus on the residues. So we're back to 0. Now alpha takes us, let's say here, and then beta takes us, let's say here. So if we don't think about this in more detail, and just distribute the mod n, we can do that independently, but then we're ultimately granted something that could be greater than n because we went around, n and then more than n, but we can't do that. So we know that since this is the final position, you must have a mod n applied at the end of all this arithmetic to truly yield the final answer, which should be, like somewhere around 3 or something in this visual. So with this logic, we can conclude the following, that a plus b mod n is alpha plus beta mod n, which are the residues, and then that could be written as, alpha plus beta, each being the residue, but then you have to mod n at the end, just like you have to mod n here. So you can't get away with just distributing this and getting alpha plus beta. You have to mod n it at the end to make up for the fact that you could be going around more than once. So the third thing that we want to look at is this equation, or this sort of statement. So this one is not so obvious to approach, right? Because who the heck's going to know what to do with a modulus in an exponential case? So there isn't really like an associative or a distributive analogy to normal division that we can reference in this case. So Let's try to take the same approach as before. Maybe it'll work. So let's try to break it down, see what we can get. So we go ahead and write A as we've been writing A as n I times n plus the residue alpha. And we'll leave B as B. We won't really break it down because we'll see that we don't really need to. And then, mod n. So this inside the parentheses looks kind of like a binomial expansion candidate, because if we recall from the binomial expansion, that some general number x plus some general number y to some general number z, all of which meet our criteria of being non-negative integers, is equal to the sum over some index k from 0 to z of z choose k. This is z choose k from Pascal's triangle, times x to the k times y to the z minus k. So this is the standard binomial expansion that most of us are familiar with. And so if we apply this to this instance here that's inside the parentheses, or actually the whole thing, then we'll get, I'm using square brackets now just because there's a lot of parentheses involved, but they mean the same thing. And I'm using square brackets to delineate originally what's inside this. So we have the sum going from 0 to now b, not z. And so it's going to be b choose k. And originally what was our x is now in, so in to the k. And then originally what was our y is now alpha, so times alpha to the b minus k, because originally it's z minus k. And all of this, mod n. So kind of not super obvious, but it is mathematically true. So let's see what we can get from that. So this is just re-summarizing what we got to before. So we're here. And now we need to note that virtually every piece of the product inside the sum yields a simple whole number. So what do I mean by that? B choose k, this piece of this product of three things here, returns a positive integer per Pascal's triangle. So it could be, like 1, 3, 4, 6, whatever. So it's just a positive whole number. And then this part here, alpha to the b minus k, is basically an integer power of an integer, alpha being 1, and then these two also being integers. So it's just another whole number. And then this part in the middle could be broken down into I to the k, n to the k, where I to the k is, as above, a whole number. So I is, an integer, an index, and then raised to the power of another index. Again, just a whole number. So let's collect all of these integer terms as one whole number, constant, dependent really on whatever k is that we are at the sum, and we'll just call that ck. So then the above kind of nasty looking thing boils down to this, where all these terms except the n to the k, which is left here, I'm just calling c to the k, because they're really all just a bunch of whole numbers multiplying each other, so it's just a constant. And so this is the same as above, because we're still summing and we're still doing mod n. So now let's think about what we have so far here. As a sum, this will have some power of n in every term except the first term, where n is raised to the 0th power and thus yielding 1, right? Because this sum starts at k equals 0. And so the first term here will just be c of 0. And then after that, plus c of 1, n plus c of 2, n squared, plus yada, yada, yada. But the first term doesn't have an n. It's just c of 0. And so that's critical to sort of realize. So referencing our sum property, which is the second equation that we highlighted because it's pretty important, we realize that the total modulo is the modulo of each term and then a final modulo. So, the total modulo of everything here is the modulo of each term and then a final modulo appended at the back. So in that case, we realize that each term with any power of n times an integer, so basically any term except the first, where it's n to the power of 0 and the n goes away, will have a mod n of 0. It will not contribute to the sum, because every term is just going to be some whole number times some, power of n. That's just going to be a bunch of n's. So you're going around the circle 100 million times, whatever, but you're still back to 0. So really, we only need to care about the first term, which doesn't, possibly bring us back to 0. It's just C0. Everything else in the sum is just a bunch of full revolutions around the clock that will yield us nothing. So going back, this was our original equation. And now we can see, I'm just bringing this part, which we had before, down here. And now I'm saying that after we realize that the only thing that matters is the first term, this is going to be equal, because everything else 0, is going to equal to just the first term. So now it's b choose 0, this to the 0th power, and then here b minus 0. So basically k is 0. And then this boils down to the following, because b choose 0, anything choose 0 is 1. You only have one choice, which is to choose nothing. And then here, anything to the 0th power is 1. And then we're just left with alpha to the bth power. So that's that. And then we carry on the modulo n at the end. So this is our third property, which is crucial for the mathematics behind the Diffie-Hellman exchange, which is, it's, not at all trivial. Who would have thought this? But interestingly enough, any number a to the power of b modulo n is equal to the residual of a, alpha, to the same power of b modulo n. So here's a summary of our properties. For those familiar with modular arithmetic, you may know these properties. And so then you can just kind of like watch from here how it applies to the Diffie-Hellman exchange. But in general, there's no way I would have guessed these. So I thought it was pretty cool to walk through how we got them. So now we want to understand the Diffie-Hellman exchange context. So again, I sort of assume that you're kind of familiar with it, so I'm not going to go into detail about its process, but in general, two parties, Alice and Bob, will exchange two numbers. So these we'll call n and g. And usually these have the properties that they're large, coprime, etc. for the extra security, but the math holds as long as they are positive integers, so they could be anything, and the math will give us the same answer. So the general premise is for Alice and Bob to generate the same key without an observer that we'll call Eve, who has access to all the exchanged parameters, being able to generate the same key. So Eve is, listening into all the transactions between Alice and Bob, and the question is, can they come up with the same key so that someone who's listening to every transaction that they send each other cannot come up with the same key? So currently all three parties know n and g, because we said that we'll exchange these two numbers. Someone will make them up and then send them to the other person, and obviously that was eavesdropped upon, so everyone knows n and g. So the procedure goes as follows. Alice takes n and creates a private number a, so she does this in her own computer, her own domain, no communication about it, which is a random integer between 1 and n. And Bob does the same to create b. So a and b are just two random numbers, somewhere between 1 and n. That's it. So only Alice knows a and only Bob knows b. These two numbers are never exchanged. So then Alice computes the following quantity. She takes g, which is known to both, raises it to the power of a, her private number, and then mod n. So we can call this quantity, the same quantity, I'll just go ahead and call it gamma of a, since we know this number will be some form of residue. It'll be less than n, because we're taking, mod n, so it can only be up to n minus 1. So it kind of has the properties of a residue. It is, really. So I'll just go ahead and call it gamma of a. This is a subscript. It's not to the power of a. So Alice sends this residue, we'll call it, gamma of a for Alice, to Bob. And Bob does the same thing. So he computes g to the power of b, his own private number, mod n, and he gets some form of residue. We'll call that gamma of b. And he sends this one back to Alice. So at this point, Eve knows n, g, and the two exchanged residues, but not a or b. So at this point, Alice takes the gamma b sent to her by Bob, and she computes the following. So she takes this gamma b, raises it again to the power of her private number a, and then whatever this quantity is, she takes mod n. And so this is equal to, just to remind ourselves, Bob's original gamma b was g to the power of b mod n, and so Alice is taking that, raising it to the power of her a, and then doing mod n on that. So here's where we need to invoke our third property to sort of make sense out of this one, because it wouldn't, otherwise you wouldn't really see how this A can be transferred over to, here, or anything. Like, how would this A work when there's a mod here, right? So it's not intuitive. And when we take a look at this result that we've shown is true, then we notice the following. So here, this is just this. So we're trying to compute this. Remember, Alice is taking Bob's residue, raising it to her power, and then doing mod n. So what we notice is that this here is the property of a residue, right? That's why we called it gamma b. And so it's similar to alpha in this property here. And what this formula is telling us is that when there's a residue raised to some power, mod n, it's as if you're raising the original number, um, which we got this residue from, to that power, and then mod n. So interestingly enough, we remember we got this residue when we did g to the b mod n, and so this is kind of the original number a that or pardon me, g to the b here is sort of the original number a, from which when we do this mod n, we get the residue gamma b from. So when we plug this in, gamma b as alpha here, then this implies that the a should be g to the b. And so now when we get that, now we know that g to the b here is going to be raised to this exponent. Here it's called b, but here it's called a, so it's the same exponent. And here it's going to be mod n, because both sides have to have mod n for this relationship to work. And now we know whenever you have a quantity raised to an exponent, you can just multiply the exponents. And so this is g to the ab mod n. And that's in red because that's ultimately the key number that both parties are going to get to the same value. So now Bob does the same. He takes his gamma A residue sent to him from Alice and computes gamma A. He now raises it to his own private number B as opposed to A from before. And again, mod n. And so he notices through the same relationship, or he might not notice, but what ends up happening is through the same relationship, this residue here, which was represented as alpha here, is equivalent to its original number being raised to the same power, mod n. So the same number that we got this residue gamma a from is just ga, and so that raised to the same power b, mod n. Now we multiply the exponents because we're raising it to the power of that, and so we get the same exact answer, g to the ab mod n. These two are in red because these are what the key should be. So they both arrive at the same number, which they can agree to be their common key. And the kind of critical point here is that Eve is not able to arrive at this feasibly. And what we mean by feasibly is that if n is big enough and such, then it would take a ton of computational power to try to brute force your way into finding this. And the reason for that is really, the secret's through the modulo, because of this clock. So whenever you have something going around this clock and stopping somewhere, you really only know the end point, right? Like, okay, if I take a clock and I spin it and it lands at 3, I could spin it from a different position and it may still land at 3, right? It could have been 12 and I go spin it and it ends up 3, or it could have been, 7, I spin it, lands at 3. So the fact that we have kind of this redundancy, or the fact that we're exchanging something that is, processed through something which can have multiple initial states end up at the same last state, makes it really tough to go back and ask what truly is the initial state. And so it's kind of amazing that this math works out. So that's kind of what I wanted to show you. And here is an example that I kind of wrote in Python just to show you that this works for any number. You obviously don't need to know Python. I'll just explain what I'm doing here. But it's pretty cool and shows that this really does always work. No need for primes or anything like that to make it true. So this is just the random module which we can use to generate some random numbers. So I'll run that. And here we want to define our n. It could be anything. I'll just make it some random number like this. And g whatever. We can make also another random number. So we'll run that, and those two are stored. And now we go to Alice's domain, and Alice will be generating her a. Remember, it's a random integer from anywhere between 1 up to n, which they both share. And then she'll take g, raise it to the power of a, and Python uses these two asterisks to mean to the power of. Most programs use a caret or like a hat, but Python doesn't. And then that answer she'll take modulo n, and we'll call that, kind of gamma looking. I used y, but gamma a. So we'll do that. And let's just go ahead and see, what that random a was. So turns out to be this. Cool. And then what that gamma a was. And it turns out to be that. Okay, cool. So Bob does the same exact thing. He generates his own b from a random integer that he picks anywhere from 1 to n. And then does the same procedure. Takes g, raises it to the power of b, and then modulo n, which he'll call his gamma b. So we do that. And we should expect b to be completely different from a, right? So is b equal to a? It's not, as it should be. And then yb should also be probably completely different from both. So it's just a bunch of random looking numbers. And so now Alice gets the yb that Bob sent. She raises it to the power of her own private number a, as we mentioned, and takes the modulo n. And here we get this number, which, interestingly enough, when Bob gets his YA from Alice, raises it to his own private number and does modulo n, happens to be the same exact number. So here it's just asking the question, is this here equal to this here? And yes, it's true. So, we can see this. I'll clear the outputs. We can see this for any number, right? So like just pick another number and then, like another number. Run it, run it, run it, run it, run it. Same number. And, n could be small, big, it doesn't matter. G could be small, big, it doesn't matter because we just showed, I'm using a bunch of 2's. Let me use the other side of the keyboard. So, yeah, the math will always hold in general. So I thought that was pretty cool. If that was helpful, hopefully hopefully it was helpful for someone, because I didn't really completely grasp the nuances behind the details of the Diffie-Hellman math from what I have seen so far on different videos. So I thought just to kind of like share my own conclusion as to how I arrived at this making perfect sense, which is pretty cool that it's implemented in almost anything. So thanks for watching, and appreciate your time, especially if you went through the whole thing.